All right. Welcome back, everyone. We're going to start the session. As we start, I'd like to remind you that at this QIP, we're blessed with massively parallel sessions. So this is a complexity theory session. So if you're a seasoned complexity theorist, please leave the room and go next door, learn about onions and matrix product operators. OK, no one's leaving, so I imagine there's no complexity theorist in the room, except hopefully the speaker. So good, because if you're not a complexity theorist, you're in for a couple treats. Two very nice results in complexity theory, and the first one is going to be presented by Henry Ewan from Berkeley, who's going to tell us about parallel repetition for entangled games.
All right, thanks, Thomas. So yeah, I'll jump right into it. So first, I'm going to tell you about what entangled games are. Probably many of you have seen this, but if not, it's a very nice game. So the setting we consider is that we have two players. We call them Alice and Bob. And they're not allowed to communicate. But instead, they interact with this scientist or a referee. And they're going to play the following game called the CHSH game. And in this game, what the referee or the scientist does is sample x and y, which are uniformly random bits. And she sends x to Alice and y to Bob. Okay? And what these players are supposed to do is that they come up with bits A and B, and they send these bits back to the scientist. And the scientist checks if the XOR of these two answer bits, A and B, is equal to the AND of x and y. Okay? And if that's the case, we say that the players win. And so you might ask, well, what is the maximum probability that the players win in this game? So if the players are classical, meaning that how they generate these bits is using some deterministic strategy or some strategy that might use shared randomness, their maximum winning probability is 3/4 or 75%. And they can accomplish this just by sending zeros all the time. They just ignore their questions. But it turns out, fortunately, that if you now allow these players to share quantum entanglement, they can actually play better, do better in this game. So when they receive their questions, they make some joint measurements on their entangled state to create these answers. And their maximum winning probability is better. It's actually 85%. Okay? And we call this the maximum classical winning probability we call the value of the CHSH game. And when they use entanglement, we call this the entangled value. Okay? We denote it by val star of this game. Okay? So one way of phrasing the famous Bell's theorem is that the entangled value of this CHSH game, this very simple game, is strictly greater than the classical value. So using quantum entanglement, players can achieve stronger correlations than they can classically. OK. So now I'm going to consider a variant of the CHSH game. I'm going to consider its parallel repetition. So what is this? This is another two-player game. But this time, the referee is going to sample n independent question pairs, x1 through xn, yi through yn. They're all uniform and independent of each other. And the scientist is going to send all of the x questions to Alice and all of the y questions to Bob. So they see all these, this n tuple of questions simultaneously. And they win this new repeated game if, for each I, they satisfy the original game-winning conditions of the original CHSH game. Okay. So they're playing this n copies of the CHSH game in parallel. So the natural question to ask is, well, what is the maximum winning probability in this new repeated game? Okay, you can ask, well, what if they are classical, or what if they share quantum entanglement? How well can they do? So, so here's an easy observation. Well, it's clear that in either case, whether they have classical strategies or quantum strategies, their success probability is at least the original success probability of the single copy of the game raised to the nth power. And why is this? Well, the players can simply play each round independently, right? They can just treat each game independently and just play the game as they would normally. And so they should win with at least these probabilities. So you might think, well, what about the other direction? I mean, surely the inequality holds the other way, because what else can they do? The questions that they receive are all independent of each other. They have to essentially play each game independently, right? Well, I'm going to make this a little interactive. So exactly one of these two statements is true. Okay, so who thinks that if they are allowed classical strategies, that their maximum success probability is 3/4 raised to the n? I mean, who thinks this statement is true? Okay, all right. What about the second one? All right. Cool. So it seems like people might have seen this before. It turns out that this one is false, but this is actually true. So the reason for this one, if they're allowed quantum entanglement, they can actually, their best strategy is to essentially play each game independently, and this is due to a very nice result from about 10 years back by Cleve, Slofstra, Unger, and Upadhyay, which says that if you take an XOR game, the CHSH game is one example of this, and you repeat it n times in parallel, and you look at its entangled value, it turns out that the entangled value of the repeated game is exactly the original value, entangled value raised to the nth power, like you might have expected. And this is because the entangled value of XOR games has a very nice STP characterization, and this STP tensorizes under parallel repetition. Okay, so here it seems like the entangled value of repeated games behaves very nicely. But this is kind of strange. So this is not true. And in 2014, Ambayanis showed that actually if you repeat this game n times and you take the limit of the classical value of this repeated game and you take its nth root, the value converges to 0.809, which is greater than 0.75. Okay? So something weird is happening. Somehow, even though you're playing n independent parallel copies, the players can do better. Okay? So something interesting is going on. So this is a more general question you can ask. Well, what if we talk about games other than the CHSH game? Let's talk about a general two-player game where the questions aren't necessarily bits. They're not necessarily independent of each other. They're just drawn from some joint distribution pi of x, y. And the winning condition is just defined by some verification predicate that depends on the questions and the answers. Okay, so a general two-player game is like this. And then you can ask, well, what's the relationship between the entangled value of the repeated game and the original game? Right, as we saw, parallel repetition is quite weird. And to give you maybe a very high-level intuition of why it's strange, it doesn't behave like you would expect, is that probably many of you have had this experience when you're taking an exam. Sometimes, if you look ahead at later questions to try to get hints about how to answer the previous questions. And sometimes you can do better in an exam that way. And I've certainly used this technique a lot. So given that it's weird, what do we know about parallel repetition? So here's what we know in the classical case. So there's this theorem called the parallel repetition theorem due to Ron Raz in 1995. And it talks about the classical value of two-player games. It says if you walk up with the game that has a classical success probability 1 minus epsilon, and you repeat it n times, then the value of this repeated game decays exponentially. Okay, but at this very strange rate. There's this epsilon to the 32, and then there's this S factor, which is the length of the player's answers. But it does show that for non-trivial games, the repeated game value does go to 0 exponentially fast. But we know that actually it can't be exponential in n. There has to be this epsilon raised to some power, at least epsilon squared. And there has to be this dependence on the length of the player's answers. Okay. But this theorem was extremely influential in classical theoretical computer science, and it's been used in probabilistically checkable proofs, the hardness of approximation, communication complexity, many other things. And it's not an easy proof to show this bound. Okay. So what I'm going to talk about is trying to prove a quantum version of this theorem, where instead of the classical value, we talk about the entangled value. So this theorem assumes that the players don't share entanglement. So the question is, well, what if they share entanglement? Does such a bound still hold? Okay. And this is a subject that has been looked at extensively over the last 10 years. And what people have been able to prove is are parallel repetition theorems for many special classes of games. I won't go through, I won't define what these games are, but over the years, people have established that there is some sort of a form of exponential decay for broader and broader classes of games. But unfortunately, for a while, there was no proof of decay for general games. So in other words, up to this work, for example, we still didn't know that there could be an example of a two-player game where its entangled value is, say, 0.99. But if you repeat it in parallel for n times, for any n, that maybe the entangled value of this repeated game just always stays above some constant. Okay, which seems which would be very bizarre, but we didn't have a proof that this couldn't happen. So what this work shows is actually that cannot happen. There is some decay. So the main result is if you walk up with a two-player game that has entangled value 1 minus epsilon, and you repeat it n times, the entangled value of this repeated game decays like this. So it's a little different this time. It's essentially it's a inverse polynomial decay. So as the number of repetitions goes to infinity, the entangled value goes to 0. Not quite at an exponential rate. We weren't able to prove that. But this is the first decay bound for general entangled games. And this is, in some sense, a quantum analog of Verbitsky's theorem. So what is Verbitsky's theorem? So before Ron Ross proved his classical parallel repetition theorem, people were working on this question in the classical case. And Verbitsky gave the first proof that the classical value of repeated games goes to 0. But he showed some, not an exponential decay, but he showed some decay. So this is sort of a quantum analog of that. Okay. All right. So I'm going to give a proof sketch. So how do you prove a parallel repetition theorem? I mean, you want to show that when you repeat this game in parallel, in some sense, the game gets much harder to win, right? Because now instead of having to answer one set of questions, you have to answer n instances of the game. So the proof is by contradiction. So you start by assuming that there's some super good strategy for this repeated game. Okay, so what's a strategy? You assume that Alice and Bob share some entangled state, psi, and we know nothing about this state other than it's a bipartite state. It could have, its dimension could be, it could be anything. And their strategy is to, when they get a tuple of questions x1 through xn, they just apply some, Alice applies some POVM on her part of the state, and Bob also applies some other POVM B that depends on the tuple of questions that he receives. And the distribution of answers that they produce is just governed by this, this formula. Okay. So this is just some strategy, and you assume it's super good. What that means is that you assume that under this strategy, the entangled value of this repeated game is much greater than this target bound we're trying to achieve, this inverse polynomial bound. Okay? So we just assume that. And the goal is to obtain, now you want to convert this into a strategy for the single copy of the game, whose success probability is greater than the entangled value of this game, which would be a contradiction, right? So how do we do this transformation? So you say, well, if the entangled value of this repeated game is too large, then there exists some nice event W sub s. Okay? I'll explain what that is in a second. But under this nice event, the probability that these players win the ith round for an average I is greater than the entangled value plus delta. Okay? So, and what is this nice event? It's just winning in some small set of rounds S. Okay? And this is not too hard to show. As you can show this without thinking about anything quantum. So if you've identified such a coordinate I, such that if winning I conditioned on this event is greater than the entangled value of the original game, then you have a good start, right? Because then the idea is to create this strategy for the single copy of the game. We want to embed the single copy into the ith round of the repeated game conditioned on this event. And you want to do this embedding without communication. So in pictures, though, this is what it looks like. So the referee or the scientist samples a question x star, y star from the original game distribution pi, sends x star to Alice, y star to Bob. And now in their heads, what they're going to do is they're going to think, they can't communicate, but this is what they're going to try to coordinate, is they're going to think, let's pretend that we're playing this repeated game conditioned on the fact that our ith questions in this repeated game is x star and y star respectively, and this event W sub s. Makes sense? Okay. So this is also something you do in the classical case, and they do this embedding, and it requires a very careful conditioning of probability distributions. Okay, and this is part of what makes the proof of Rawls's theorem non-trivial, and so. But in the quantum case, it's very hard to carry out the same program that Ron Rawls carried out. So. And as many of us know, the notion of conditioning quantum entanglement is very risky and very dangerous and not recommended if you don't know what you're doing. But we're going to try to do it anyways. So this is what we're going to do. So for all x star and y star, these are questions from the single copy of the game. We're going to define an advice state. So this is just some bipartite entangled state, phi, that depends on x star and y star. And this state intuitively represents the repeated game conditioned on these two things that we wanted to condition on. So imagine that we were somehow able to define this kind of advice state. So what would they do? And also let's imagine that upon receiving x star and y star, the players generate this advice state using pre-shared entanglement and local operations. So they receive their questions using local operations. They transform some pre-shared gamma into this advice state or some approximation of it. And then they perform some local measurements on this advice state. And what they're going to get are answers A and B that satisfy the original predicate with probability, this probability, which is the probability that they win the ith coordinate conditioned on this nice event and their two questions. And if you now average this winning probability over the choice of x star and y star, this is going to be approximately the probability of winning the ith coordinate conditioned on w sub s, which we've already identified as being this amount, right? So now they've won the original game G with probability higher than val star of G. And this is our contradiction. Okay, so that's what we're going to try to do. So, okay, so how do we define this advice state phi of x star and y star, and how do they sample it without communication? Okay, so this is the main challenge in proving quantum parallel repetition theorems. And the main problem is that, I mean, this state depends on both x star and y star, right? And in non-trivial ways. So the main problem is that Alice doesn't know y star, right? Because she's not communicating with Bob. She doesn't see what input he gets. And Bob also doesn't know x star. So neither Alice nor Bob knows the full description of this advice state. Okay, so how can they possibly sample it? So the solution is we're going to show that there actually exists local unitaries. So a local unitary on Alice's side that only depends on her input, and a local unitary v sub y star that Bob uses that only depends on his input that transforms this advice state to some universal state gamma. Okay, right? So if we can do that, then they can sample it. So here's how we define this advice state. And we're going to do it in 3 easy-ish steps. So imagine that Alice and Bob play this repeated game using this super good strategy that we assumed. Okay, so they start with this entangled state. It lives in this space E sub A, tensor E sub B. And Alice gets all these questions, and Bob gets all these questions. But let's imagine for the moment that Bob actually just holds off on his measurement. He doesn't apply his POVM, and only Alice measures. Okay? So she measures, and she generates her answers only for the rounds in S. So she only cares about her answers for the S coordinates. So now let's just look at this system as a whole. And let's just think about the global state of the system. So we have these registers X, these registers Y, and this A sub S. These are all classical registers. They represent the inputs and outputs of the system. But we also have this EA and EB. And in these registers, we have the quantum post-measurement state. But again, only when Alice makes her measurement. Bob hasn't done anything yet. Okay. So the first step is to show that in this global state rho, the quantum mutual information between an average coordinate xi and Bob's part of the entanglement conditioned on the answers that Alice generated and Alice's questions in these coordinates s is small. Okay? And it's less than the size of the number of the size of this set S divided by n. And you prove this statement using an application of the chain rule. Okay? Intuitively, what is this saying? It's saying that when they carry out this process, from Bob's point of view, I mean, he only sees his part of the entanglement. His part of the entanglement doesn't have much information about the ith coordinate of the ith question that Alice receives. Okay, conditioned on a particular answer that Alice produced. Okay, so that's step number one. Okay, and so we're going to think of this as small because S, think of it as like square root n or even log n. So this quantity decays like 1 over n-ish or 1 over square root n. So the next step is to say, from this fact, we can conclude that for every x, we can define a purification of Bob's part of the entanglement. So look at Bob's state. It's some mixed state, rho EB. And we can define this purification delta sub x such that conditioned on Alice's answer and her ith question being some little x, these two purifications the purifications are going to be roughly the same for most x and x prime. Right? This is really just kind of a restatement of this fact that that Bob's state really doesn't depend too much on x sub I. Okay, so now we're going to define our advice state. And here's where he's going to come in and actually make his measurement now. So we take these purifications, and Bob's going to make a measurement. But it's kind of a funny measurement. It's his original POVMs, and remember that his POVMs depended on n questions. But in reality, they're just playing the single copy of the game. So he only has access to some little y. So we're going to take his original POVMs and just average them over all possible choices of yi through yn, except in the ith coordinate, we're going to fix it to the real question that he got, this y star. Okay? So this is just some POVM, and we're going to just apply the measurement on the purification. And we're going to we're going to normalize it, make it the proper state. Okay, so that's our advice state. So why is this advice state useful? Well, I'm going to claim that this state kind of represents what we wanted originally. We wanted something representing the repeated game, conditioned on the fact that in the ith round, Alice and Bob received some questions x star and y star. Okay, so and it does. So Bob received y, and he kind of takes this average over all these other questions. Alice received the question x, and also this state is also represents the original game, the repeated game conditioned on this event w sub s. That's because we're fixing these answers a sub s and b sub s. And if you fix these answers to be winning answers, then you've also conditioned on them winning in the coordinates defined by s. Okay, so that's nice. So it kind of represents what we wanted, but how do we know it's sampleable, right? We wanted that Alice and Bob, without communication, can generate this advice state. Okay, so the third step is to argue this. Well, we defined this advice state, and we knew before Bob's measurement these two purifications were close. So how far can these states be driven apart when you smack on this POVM? And it can't be that far, because one thing you can crudely do is to say, well, it's the original distance between these two states divided by the probability of the norm of this state, right? Which is the probability of this event w sub s. Okay, so right. Okay, so for most x and x prime, the advice state where Alice and Bob get x and y versus the advice state where Alice gets x prime but Bob still gets y is not that different. Okay. So in other words, this advice state, when you fix y, is not sensitive to what question Alice gets. Okay. So let's look at this expression and note that the probability of winning some number of coordinates s is always going to be greater than the probability they win all the coordinates. So we have this inequality. So let's just plug that in. And what we get, and what delta was this s log, it's s over n raised to some power. And so we want to show that this distance is small, and that's small when the probability of winning all the coordinates is greater than this quantity. But by our assumption that we had a super good strategy, this is the case. And so let's, if you choose the parameters right, then this distance is at most square root delta. Okay. So basically, we're done. Why are we done? Well, we invoke this thing called the quantum correlated sampling lemma of Denur, Storer, and Wittig, who used it to prove an earlier parallel repetition theorem. And it says that when you have these two conditions, that this advice state is, if you fix y, it's insensitive to the value of x, or if you fix x, it's insensitive to the value of y, then we do get these local unitaries that we wanted originally. So if we start with something called the embezzlement state, Alice and Bob can apply local unitaries that only depend on their questions to generate this advice state, and which is what we wanted. Okay, so if that wasn't, if you didn't follow totally, that's okay. Basically, the punchline is that they can really generate this advice state that we wanted and achieve a contradiction. They can win the original game G with too good of a probability. So going back, this just meant that there wasn't a super good strategy for this repeated game. Okay, so that's it. What we showed is, just to summarize, is a quantum analog of Raz's classical parallel repetition theorem, but with polynomial decay. So this is the first general decay bound. What if you wanted exponential decay? So this is still an open question for general games. But if you don't really care about, say crypto applications or complexity applications, if you don't really care about the game G to then exactly, but you just want some sort of gap amplification, and you can tweak the game slightly, and then repeat this tweaked game, you can actually get exponential decay. And this is something that we talked about at last year's QIP. This was joint work with Bavarian and Wittig. But it's still a nice question for, what if you don't tweak the game, just the general case. Okay, so I think I'll end here.
We have time for questions.
Does your result work for more than 2 players? And you're mentioning it there, classical, but the one you were just talking about, does it work for more than 2 players?
Right. It does not work for more than 2 players.
Can you say why?
Oh, because I glossed over this, or I didn't cover it at all, but part of the proof also uses the classical correlated sampling lemma, and that is, we don't know to work for more than 2 players.
Thanks.
Yeah.
There was another question just over there. There was a question, someone? No? Okay. Other questions? I mean, I have a question. It's not fair, but so what's preventing you from getting exponential decay in yours? I can see the step where it's happening, but do you have a high-level picture to give us, or an idea?
Yeah. Yeah. So, I mean, I guess. So one way of looking at it is, I had the step where I said, well, let's imagine that Bob didn't apply his measurement. Let's only analyze Alice's measurement. And that was kind of the barrier, because normally you'd want to, in reality, they do apply their measurements simultaneously. So you'd like to analyze, this situation where they both apply their measurements. But somehow when they do that, it's very hard to understand the correlations that are introduced between their questions when this happens. So the workaround was to say, well, let's imagine that only Alice applies her question, but then when you say, well, let's add Bob's measurement back in, then you have to divide by the probability. Yeah. So yeah, but I'm not really sure why.
Yeah.
So you showed that when you have this quantum correlation, you have the upper bound that you prove. What about what about when you have non-signaling correlation instead of quantum correlation? Is there such a bound?
Yeah, so actually for non-signaling games, there is an exponential decay bound known. And it's, the proof follows, it's pretty similar to the classical case. Yeah.
Is there any one last question? Yeah, we have a question over there. Last question.
I was just curious if it's possible to point to the steps which allowed the generalization to general games beyond like free games and those other classes that you pointed to.
There wasn't really one main step other than, I mean, the main idea was this separation, like considering Alice's measurement and then Bob's measurement. But other than that, there were just a bunch of like technical hacks to get the proof to work. So, yeah.
I think that was pretty modest. So let's thank the speaker. Let's thank Henry again for his talk.